This is just a short video on all the characteristics of polynomials, and I like things in a table, so I made this table. This is in the front of your note packet that you can go through to look at what are the characteristics of polynomials. So at the beginning here, I'm going to tell you that when we talk about polynomials, remember that it's many power functions together, and we already talked about how do you tell what the power is of the largest power is the power of the polynomial. So if I look at any polynomial, the highest power tells you the number of roots that are in the polynomial, where it crosses the x-axis, or zeros if you will. If the power is even, I know it's an even degree. If it's an even degree, I know my tails are in the same direction. Okay. The leading coefficient is of the one of the highest power. If the leading coefficient, that's what this stands for, is positive, then my right tail will go up. So we'll go in that direction. If my leading coefficient is negative, my right tail will go down in this direction. Okay? And the number of turns, the nth degree, means that the turns are, there's one less turn. So that means there's n minus 1 turns. Okay, so this kind of tells what's going on in each category. So what I'm going to do for each square is to actually show you kind of a graph. But let's do this part over here. So if I'm doing a quadratic here, which is a 2, I'm going to have just one turn in my graph. So let's do a sketch. And I'm going to make two graphs here. And let's put some colors in this so it looks a little decent. So I'm going to make this one red. So I'm going to give you an example of a quadratic. So if the leading coefficient is positive, and you guys know this, that if the leading coefficient in front of the x squared is positive, it's a smiley face parabola. Well, the reason why is because if the leading coefficient is positive, my right tail goes up, and because it's positive, both tails go in the same direction. Now here, if my right tail goes down because of leading coefficient and it's even, they're both going to go in the same direction. So here's an example of what that would look, and you see the one turn. Okay, now we're going to talk about end behavior. End behavior, you're talking about what's happening with your tails. So here I can say as x approaches infinity on this side, my y is also approaching infinity because it's going to positive infinity. And here, if my x approaches negative infinity, my y is going to approach positive infinity because it's still going up. Okay. On this one over here, as x approaches infinity, my y is approaching negative infinity because it's going down. As I go to the left here, or if I'm approaching a negative infinity, my y is also approaching negative infinity. So now we have a picture of a power of 2. Now that's just an example. It could look different. Okay. So let me go back to the black here so that we have a kind of the same thing here. So now we're going to talk about a cubic. Well, I have an odd degree because the power is odd. If I have an odd degree, my tails are going to be in the opposite direction. Okay. Now, if my power is 3, I'm going to have one less turn, so it's going to be 2 turns. Let's set this up again like we did above and make a couple graphs of what an example of a cubic formula would look like. So I'm going to change my pen color here so it'll make this one look a little different. So I'm going to pick one. Now, I'm still in this column even though you can't see the top, but if the leading coefficient is positive and the right tail goes up, and the tails are opposite, it's going to look kind of like this. Because the tails have to be opposite, and because it's positive, the right tail goes up. In this column, even though you can't see the top, I can say the leading coefficient is negative, so the right tail has to go down, and my tails are opposite over here, so that means it's going to look a little bit like this. Okay, for an example. So let's talk about the end behavior of my tails in this case. Well, here as x goes to positive infinity, as I go to the right, my y's are going to positive infinity. Here as my x's go to negative infinity, as do my y's go to negative infinity, because the tails are opposite. Over here, as I go to the right, as x goes to positive infinity, my y's will go to negative infinity. Here, as I go to the left, as x goes to negative infinity, my y's go to positive infinity because they're opposite. Okay, so now we just did a cubic. All right, let's try the next one here. I'm going to go back to black, so this makes this look nice. And I'm going to make a x and y axis. Might as well set that up right now. Actually, I'd do the whole paper if I could see it all at once. Okay, and it's Quintic, so I have an even power or an even degree. If I have an even degree, my tails are the same direction. Okay, and since I have one less power, I mean one less turn, I know there's going to be 3 turns to this graph. Okay, so let's kind of do an example. I'll make the color different. Let's pick green this time. Okay, so in this column at the top it says my leading coefficient is positive. So that means my right tail has to go up, and since the tails are in the same direction and I have to have 3 turns, it's going to kind of look like this. Like a W. Okay? And here, because this column says my right tail is going to go down, since they're in the same directions, it's going to kind of look like this. And I have to have 3 turns in it. So it's going to kind of look like an M. Okay? Let's look at our end behavior. As x goes to the right, or positive infinity, my y goes to positive infinity. As x approaches negative infinity, my y's approach positive infinity. Over here, as x's go to the right, or positive infinity, my y's go to negative infinity. As x approaches negative infinity, so do my y's. Okay? One more. So we've done, so far, let's look at what we've got here. Oh, it's so pretty. All right, we have quadratic, tails in the same direction, 1 turn, and we talked about the end behavior. We've got cubic, where it's an odd degree, so my tails are opposite, and my right tail goes up if it's positive, and right tail goes down, and since they're opposite, it looks like that. Another even degree, which is Quintic, so the tails are in the same direction, if you'll notice that, and I have to have 3 turns in it. And now we're going to do Quintic. Now Quintic, let's go back to black here so you can see this nice, is a odd degree. Sorry about that, odd degree. And if it's an odd degree, I know my tails are going to be in the opposite direction. So let's set this up. Oh, and I know I'm going to have 4 turns to my graph. So this is going to make this one. I actually like to think about this when I draw this. So let's do our x and y axis. Okay, have our graphs. And I'll change the color of the graph just to make it look nice. And let's pick purple. Okay, so now I'm going to do where the tails are in the opposite direction, but this is the column where my right tail is going to go up, so it's going to kind of look like this. See if I did that right. 1, 2, 3, 4 turns. Yep. My right tail's up and my tails are opposite. Good. Let's do this one here. Yes, okay. So now that's what that kind of looks like. My tails are opposite. And this tells you also how many roots there are, so or up to that many. So now if I say if x goes to the right, positive infinity, y approaches positive infinity. As x approaches negative infinity, so do my y's approach negative infinity. Here, as x approaches infinity, my y's approach negative infinity. Here, as x approaches negative infinity or goes to the left, my y's approach positive infinity. Okay, so now you have this in the front of your packet, and it's kind of nice. It's all in one page where it kind of gives you some of the characteristics of polynomials. And if you'll notice, they're all continuous, the ones that we've drawn. And the one thing I don't talk a lot about, if you go to the top of the page, here's the number of roots. The number of roots, the maximum you can have is whatever the degree is. So here there's 2 roots, 3 roots, and so on and so forth. So that completes the characteristics of polynomials.